Docker on a daily basis? Not nearly enough. How many folks work in the cloud on a regular basis? Very cool, very cool. This helps me because I try not to dwell too long on the introductory things. And how about anybody here using Kubernetes? Very cool. We're hearing about that. Okay, well, I recently had a great little project, and I won't name the client, only out of respect, but it was a great project, and I got a chance to learn a lot about cloud technologies, and I saw how a lot of it lined up with Java, but not all of it. I mean, it's not all written in Java. So there's some great components, and I had an opportunity to put together a prototype based on this design pattern. And in that process, I thought it'd be great to be able to share with other folks. That's the thing I always loved about SeaJUG is that the cumulative number of years of experience that are in this room right now, it's amazing, right? And you think, all the things you may have done in your years of coding, and the things that you haven't done, somebody else has next to you, right? So it's always been great to come to SeaJUG to be able to tap those other brains. So I thought, hey, here's my chance to contribute a little bit. With that being said, as I had a chance to think about the cloud a bit and what the real motivation for it was, it occurred to me that somebody needed a massive internet presence and they didn't want to pay for it monthly. So they figured, somebody like Amazon, they could turn that cost center into a $6 billion a year profit center. And that's going to look, good on those quarterly reports. Of course, the rest of us benefit from that. Of course, that's all done by through economies of scale, right? We don't need to have all the duplicate data centers and all the duplicate people manning them. If you've done it right, and these big guys that have to have that already have put it all in place. So why not turn that into a profit for them? And this is the one that I always thought was kind of fun. It's really about applying the principles of RAID to the data center. So from back in the redundant array, instead of inexpensive disks, it's really commodity hardware, right? In some sense, it's about throwing a bunch of PCs at the problem and being able to scale out that way. And in part of that is also about horizontal scaling, right? So horizontal scaling is, again, throwing more PCs at the problem, not fancier ones, right? Not more expensive ones. And so writing applications can take advantage of that is the key to cloud apps. And then, being able to, another key principle here is elasticity, being able to scale out your application and be able to run it on machines on demand, and then have it scale back in. Can everybody hear me okay? I keep hitting the mic, and I don't want to use the mic. Anyway, and then having it scale back in so it's not going to cost you. I hear, I've heard a number of folks say that their data center or their cloud costs can be quite expensive. And so, being able to scale back is really important. So that's the elasticity. I almost think of it as something that's breathing. On demand is your application is breathing in and out and needs to expand. So for those, this is just some core concepts. The different types of deployments. You've got, we all know about the public cloud and the end there. And the private is being able to do that without anybody else accessing it. Start asking yourself, is that really a cloud if it's not really shared amongst a bunch of companies? But it is. Then the hybrid is kind of both, or being able to span those two. And then a community one is when there's a group of usually companies that have something of interest in common, and they pull together some things. As you're working on your cloud application, you want to look at your workloads. Is it going to be static? You're always going to have the same workload, or at the end of the month you're going to have a huge crush of things, or do you have to plan for that once in a lifetime event? How unpredictable is that workload going to be, or will it be continuously changing? Those are some different kinds of workloads and things to keep in mind when you're looking at your application. Now, I'm going to talk a little bit about cloud at first here, but I'm also going to point out how, if you're not running in the cloud, how you can take some of these things and apply them with whatever you're working on. So, I just had it right up here, but there's different kinds of services provided, right? You've got the infrastructure as a service, which is really providing you the machines to run on. Platform as a service. Anybody here use Google App Engine? Yeah. Not bad. Lots of stuff already handled for you. You don't have to think about it, right? As long as you write to their APIs. Whereas infrastructure, you can put in whatever apps you want, but then you got to maintain it, right? You're your own sysadmin in many ways. Right? And then, of course, software as a service, which you run the software. And then Ubuntu has this concept of metal as a service where you're just able to turn up metal and then be able to deploy stuff to it. And another key thing is thinking about isolation of your applications and how you're going to make sure that one doesn't interfere with the other as it goes along. And there are different ways of handling that: virtualization and containerization. And we'll get into that in a little bit. So, no matter what kind of application you're developing, there are typically these kinds of common architecture concerns, right? Things that you want to address, whether it's in the cloud or in your data center. Of course, you got to think about scalability, right? If your business is really successful, are you gonna kill it if you haven't built for scalability? Of course, there's always that balance. You build too much up front, and you kill the company in terms of cost by not delivering on time, right? So there's always that balance between doing a startup just enough to get it out the door and not doing enough that it gets killed when that big flood of business comes. Of course, you're thinking about availability and how can you recover from different kinds of failures. You kind of want to be cost aware, especially if you're in the cloud. Just a quick little story. I was playing around with an AWS account, and I wasn't paying too close attention. I was just trying to slap something together. I ended up checking in my private key into GitHub to my Amazon account and went on vacation. I get this email in Mexico. You can run up $6,000 worth of compute resources. And that was in very short order, right? $6,000. I'm like, what?
Truth comes out.
Yeah. I mean, it was a stupid mistake. 30 years of software, I ought to know better by now, but that's the truth, right? Working too fast. Fortunately, they were a little lenient with me. I reacted right away. Didn't have to pay that. But you do want to be aware of what things cost, right? The cost going in and out of your data center. Egress charges, ingress charges, storage charges, compute charges. Of course, you're going to want to be secure. Check in your private key into a public GitHub. And you're going to want to be able to make sure that it's manageable. And kind of think about that vendor lock-in, right? Where am I going to be locked in? And sometimes you know that, right? You say that's the trade-off. We got to get to market, right? That's the next slide here. Time to market. Right, so you got this time to market. Somebody's providing you services, right? And lots of great services out there on AWS, on Amazon, on Google, on Azure. So you can go ahead and use those, but you do know you're locked in, right? And that's okay. Sometimes you get to market quicker. Other times you find yourself, locked in and paying for it and don't know how to get off it because it costs too much to re-architect your application. So being aware of that is. Of course, all these things, apply on individual applications, but then when you start talking about the cloud, it's really addressed on a larger scale. And this is kind of a great little book put out by one of the guys. It's a couple of guys at Google, and they're thinking about the data center as a computer, the whole data center as a computer. And it's about I don't know if you can read it back there. Let's see. They're actually design of warehouse scale machines. So when you start talking about that number of machines in your application going there, things have to happen a little bit differently. So let's take a look at some traditional cloud design patterns, here's some sources. Here's a book. It's a university out of Europe. I can't remember the one off the top of my head, but it's a great book. And at the end of the talk, I have some links to their site. They basically have the whole book on their site. It's really well done. This is another one, great one that's free from Microsoft on Azure. And here's one, a paper written by presented by the Open Data Center Alliance. It's actually authored by several of the guys in this building at Disney. We've got Nigel Simpson is on there, C.J. Barker, Lon Kruger, I believe, authored this. So, and that was the one I kind of used for some of my design patterns that I focused on. So here's some design patterns around scalability, and I'm not going to go into all of them. I'm just going to go into a few interesting ones here. But the request queuing one is useful. You've got a bunch of requests come in, fine. You put them on a queue so you can handle them, and that way you can kind of even out your load. You can another advantage of that is you put it on a queue and then you have a bunch of workers to take the jobs off the queue and process them, and so you can scale it that way by the number of workers that are removing these from the queue. Another pattern, which is very similar to request queuing, but it's using, let's say you've got your browser and you're using a little JSON and REST, and you're gonna send documents asynchronously to a backend server, and then you'll be notified either with web sockets or by polling that something's changed, and the idea being the whole workflow is done asynchronously through queues. Pretty similar to the request queue. Another one is request collapsing. So you bring in a bunch of requests over a period of time. Let's say all the requests I get in 5 seconds. And you go, okay, I'm not going to answer them until 5 seconds has gone on, and then I know that the duplicate requests I can address. Right? So you kind of collapse all of those that are duplicates and just answer come up with the answer once and repeat that answer out to everybody that's asking. I'm kind of going fast, so I kind of want this to be like interactive, so jump in. Yeah. Perfect.
Hey, Brother Jason, I was gonna ask, so if you're requesting data, right, you can map and reduce.
Yeah, yeah.
Is that?
Yes.
Spark and Shark and Hive and Hadoop.
So you use map reduce on all your requests that are occurring in that period of time.
Yeah.
Yeah, that makes sense to me. Anybody else? Yeah, I gotta still slow. Get a little nervous up here, and it's like blah, right? Blast it out. And the way I handle nerves is I just talk about it.
So
anyway,
Jason, just out of curiosity, is this more middle tier sort of functionality you're talking about, or more on the front end side, or on the back end
so
tier?
this is about, in some sense, it's your whole system, right? So you're in certain cases like the queue-based workflow, from your client to your back end, you're going to need to make sure everybody's in sync on how they communicate. Right? Some of it's just in the back end, and how you handle all those requests coming in. Right? That stuff in the cloud. I'm not sure how much request collapsing you're going to find on your device. Maybe if you get too many UI inputs. But there's different places where you can use these patterns. The idea is these were targeted towards cloud apps. But the truth is, when you look at these design patterns, well, we've kind of seen them before, right? Before there really was a cloud. A lot of these things are just derivatives of what we already knew and have been adjusted for the cloud. Shoot.
How many, these design patterns are from scratch new applications, or somewhere migration is involved? Like, let's say there is already in-house application and people are looking to migrate that to cloud. So how much that factor influences these design?
So what I've seen is that there are already a bunch of libraries that implement these design patterns, so you don't have to go out and reinvent the wheel. In some cases, not all cases, right? So when you get that chance to redo something, and it's from scratch, you get to architect the whole thing, and you can't find a good library to do that already does it, there's your chance. I just wanted to highlight some of those that are already done, so that you can, in general, just when you get that chance, sneak one in, right? So that you make your system better, right? I don't believe in the forklift upgrade anymore. I mean, I used to think it would be great. Let's rip all this stuff up and throw it out. Let's get the no. Too expensive, can't do it. So, you know, it's agile. We do it gradually, and we continuous improvement. And we can take the same approach here. Caching is a key. Is it really a design pattern? Yeah, maybe not. But there's some great things you can do with the HTTP caching, especially if you're using REST or microservices, REST-based microservices. And I'll cover microservices a bit in a minute here, and caching. Oh, I guess I missed stateless services up there. Of course, everybody, very common, right? That's not cloud specific. The less state you have to manage in your server or your backend, the more things you can handle, more requests you can handle, because you don't have to keep track of that state. But that's not always possible.
We don't have a question first, and then
Okay.
Well, so this was going back to the key-based workflow, and I was just wondering, this is now getting into a little specifics, but I heard a very interesting podcast a month or so ago on Apache Storm, which the guy who wrote that is like, talks a lot about stream-based workflows as an alternative, for big data as an alternative to the MapReduce that has just been mentioned. And I was just wondering if you had any experience with that.
I have not. And one thing that's amazing is that there's so much technology and it's moving so fast that I knew I was going to get questions here for things that I haven't worked with, and that's a good one, right? But I did want to share what I have worked with, so folks go, okay, I kind of know what that is, or I know where to find out more about that. So, no, haven't.
But so I guess taking it away from the specifics and back to the general, the idea of, I mean, you call it key-based workflow, but I think that's similar to what Apache Storm is talking about as stream-based workflows. What have you been using? Have you been rolling that from scratch? Or you had mentioned that there are libraries that can do this for you.
So the queue-based workflow in particular is something that is actually a design pattern out of Microsoft's book. I mean, if you've done middleware, you've always done, you send documents in, you get them processed, you pass them around. So I think that might be one of those more general. On this project, one of the tools that I used that really got me to market quicker, it was a prototype, I got it out quicker, much quicker, was using Apache Camel. Right? And that's really about different, it's got nice adapters and so forth, but it really comes from a messaging-based background, right? And being able to think about connectors, pipes and streams, kind of stuff, right? So that's what I tend to use to pull those systems together, because and I didn't cover it in this presentation, but I love it because it provides domain-specific languages, right? The enterprise integration patterns are there to help you think about how to solve these common problems you encounter a lot. So Apache Camel is a great way to get there. It also has a domain-specific language for doing RESTful services, and that's really nice because you're thinking at a higher level. You're thinking in a language of solving the problem, not necessarily down in coding, so you can get more done.
Yes. So you mentioned that all these patterns have existed before cloud came along, right? So what does cloud do? Does it facilitate these in some way, or what value does it provide?
These are Docker, ways you can assure your application grows in the cloud. But maybe give me a couple slides and see if that begins to address it. Another, I don't know if it's a design pattern, but key concept is data grids. And it really takes the idea of horizontal scaling to heart, and we'll cover that too. So I take one of the scalability design patterns, microservices. We'll just kind of dig into that a little bit. So you take your application. How many folks here are developing microservices? Okay. Anybody want to know what it is? Or shall I not? Yeah, okay. So it seems a little counterintuitive, and some people, I think it's, you go to conferences and stuff, and you'll see folks going, I'm not sure. But if you take your application and you spread it out amongst many nodes, and you have one little function, and that is your service. And you have a bunch of small services. And the advantage to that, you can then apply more resources to parts of the app that need it, and when it's needed. So, what's the example I recall here? There was one on an email system, going out and finding emails. Well, one part would be about composing the email, one part might be about digging through your history of emails to find stuff. So you could then scale the search capability, search capability across many nodes, but you wouldn't necessarily need that many nodes for, say, for instance. So it allows you to take your application and spread it across many nodes and scale as you need. But probably one of the key things is allowing you to be able to change a part of the application out. So you keep everything else running, and you can introduce a new version of your component. So in this case, canary testing is the one, like the canary in the coal mine. You put the new version out there while you've got the old version still running, and you see how things go. And if you're not killing your system on those that are using the new version, then you can then begin slowly replacing the old version with the new version, and you've swapped out parts of your system. Change out your engine while you're doing 90 miles an hour down the road. Right? There are 4 parts of it.
I have a question.
Shoot.
So how do we route things? Let's say we have 50 nodes, and out of that, 40 are running the stable version of your app, and 10 nodes are running like the new version of the component. How do we route between these nodes?
Yeah.
Like whenever a request comes, how do we make a decision?
Of course, to some degree, that's going to depend on your system. So if you've got stateless services, you
load balancing for the scale group for the
Yeah.
user be in front of it.
Yeah, I mean, I think you're going to want to look at how you route things. Are there certain sets of customers you want to hit your new system? Then you might see what you can find in their requests that allow you to direct to that. So your load balancing or potentially your reverse proxies in front of your system could help direct.
Because I see that as a bigger problem, because I want, let's say, my testing accounts or some new users that I want to route to that, and I was wondering how people manage that. Like I can visualize how you can run microsystem, but I find it difficult to visualize how you route subset of traffic to
one versus the
yeah.
other. That's an interesting question. I think in general there's I'll see if I can find you the reference to it, to the design pattern that describes the canary. But the idea being generally that there is just a subset that is actually using it, and it may not be the same customers. You may get one page one time, another page another time. The next time you go back, because it's not distinguishing. But you're finding out, if it's affecting other things. Anybody else?
It was kind of on the same lines, except more at a higher level. When does a microservice, the management between multiple microservices, kind of collapse them to, where are the economies of scale from a development standpoint? And how low do you go in the microservice structure before you say, no, this is way too
This is too minute.
Yeah.
Yeah, I mean, I think that's you have to do it a little bit, and you have to, and I think in the system that I wrote, I wasn't quite sure at first, right? And it just pretty soon it presented itself, like, after I started looking at it, like, oh, okay, well, this is a component. I mean, this is a certain set of functionality, and it seems like a composable bit, and then if I broke it any further, it wasn't going to provide much value. And at first it was a little awkward, like, well, now I've got I've got on this machine and this machine the same library, but because both components share, both use that library, that felt a little funny, right? But it doesn't matter. I mean, it really doesn't matter. It's just about that functionality being replaceable and deployable individually, so you can update just that one part.
And then what about the coordination? Are you writing all the coordination, or are there coordination services available that are
And by coordination,
the communication, again, going back to the communication between two microservices and passing data?
yeah, so I think it's like you're doing any application, right? So in the case of the application that I wrote here, it was, there were 3 microservices, it was a chain of dependencies. And so ordinarily, and this is the real gotcha here, and I got a solution for it, but the real gotcha with the microservices are, you now have broken up something that used to be on 1 node, now it's on 3 nodes. You have 3 hops, for instance 3. And now you've introduced a lot of latency between those calls. So how do you address that? And
Martin Fowler had just written on his blog, full section of documents about microservices versus monoliths. That can be very good for you.
Mark Feller.
Yeah.
Dollar's got some stuff on it. And he wasn't always sure. Okay. So I'm not sure about this microservices thing. But he's got a little bit more behind it from my last reading. And this answering this bottom one, how you address that drawback, that's what led me to Kubernetes. And I'll cover that in a minute. But be aware, if you start doing microservices, you got to know you've got a solution for that before you, it's like, what? Everything's taking so much longer. Incurring that latency. How can you make sure those services are deployed in the same place? Jason?
Isn't there, what you're trading when you have services that talk to services and talk to services is that you're turning your bandwidth into latency. Are you running into, even when you have them running on the same VM, there are still speed limits there, are there not? Or are they just lost in the noise floor?
I don't think it's, well, generally, I don't think it's as bad as when you're going from physical machine to physical machine. So if you don't have control of where things get deployed, then, yeah, I think that's where you're going to see the biggest hit. So I want to talk about data grids for a minute. So, you've got some stuff in memory you want to share. Let's say you've got a web app and you've got some data that you want to share. You don't want to use sticky sessions and send your users back to the same session every time. That's a recipe for failure, right? Even if you could, you can't really do it in a lot of cloud scenarios. So you want to share that state between those nodes. And you want to make sure that you use the right tools to do that. So if you're just using distributing that data across all your nodes in a horizontal scaling fashion, so say you begin reaching the limits of that node. If you've done it right, you simply add more hardware. You add another box out there, it brings its memory in, and now overall your application has now increased the memory available to it. So that's using distributed data, again, a data grid. When you're replicating data, that tends to keep the same data across all your nodes, right? And when you have that, once you start reaching the max limits on that, you can't throw more hardware at the problem. The problem is you need more RAM. You're going to need more expensive boxes that can handle that more RAM, right? So that is vertical scaling, whereas the other one, where you're distributing data across the nodes, is horizontal, right? And you just throw more hardware.
But with the distributed, you have the problem that you need to find that now, right? I mean, is that you still need to have every forward-facing machine needs to know where all the little bits are and forward accordingly. So you necessarily need to always make the decision to have to include the additional hub.
So these products will handle that finding for you. And it's like distributed hash map, right? Okay, I'm looking for this thing, and it says, oh, it's over on this object over here, on this machine here. And yeah, you have to be careful about how distributed that gets, how far that data gets from each other, how good your bandwidth between those machines. So there is that, but at least you can scale, whereas if you're using the cache or Redis, those are not, to my understanding, they're not distributed, it's replicated. It's the same copy on each node. Anybody call me out on that one?
Well, no, but can you think
Okay,
of,
must be true then. I got a whole room full of smart folks. Just kidding. Hey, Ray.
hi, you know, the thing about it, HDFS is great in this case, where you're replicating both horizontally and vertically. You're replicating the data, it's like n times, usually 3. And you're scaling it across multiple nodes, so you don't need to think of replication as a single taller and taller stack each time you want to replicate the data, because you can replicate a shard of it, a piece of it across.
So,
Isn't that the same thing, right?
I haven't actually used that, HDFS, which is the Hadoop file system, right?
Yeah.
And if I understand correctly, it's more of a, it's more distributed.
It's definitely.
These are all in-memory systems, but
Okay.
but I think if you add more hardware, does it scale larger?
Yeah,
Yes.
you need more space, you add more file, you add more disks,
You add more disks.
or you add more data nodes.
Amdahl's law.
Then you start needing more bandwidth, right? Who said Amdahl's law?
So are you saying the data grids are in-memory, in-core data stored across?
Sorry, is it something I said? Or didn't say, I guess. So, I really shouldn't, because I don't know, but it sounds like it's more of a, it's distributing the data across. If you're just adding more disks, then you're kind of making a more of a vertical scale in that sense, because you're making your hardware more expensive. If you can just throw more cheap hardware development, it becomes more of a horizontal.
Well, it's both, that's just it.
Oh, okay. Well, then
I add another server, it's got a set of disks associated with it, it adds more storage to the cluster. I can now put more files and more copies of those files, distributed across the same rack, across multiple racks.
Yeah, I mean, that sounds very much like,
I think there are different
horizontal
use
scaling.
cases. What you are talking about is more on file systems, where these are more in memory, key value, cache.
Well,
So I think probably you
that's-
can use a combination of both. The use case is different, Hadoop, HDFS is our parallel processing, huge files. Where here is keeping, mid-size, I would say, or small-size, data sets that can, speed up, speed up your application.
Yeah, well, if you have that data all spread out, you know, add all the process.
I mean, that sounds very, very much a horizontal scale. You throw more hardware at it, I mean, more PCs at it, that know where to find that data, and they work together to get it solved. That's what you're looking for, right? That's why it's.
Well, that's what I'm thinking.
All right, yeah, and so what I used, and that's why I have it, is that I used
I have-
HazelCast and my system
sorry to-
nicely for sharing that state between my web servers.
Sorry to interrupt, but I just want to ask a follow-up question with what he asked. It's like, when we don't replicate the data for across the different machines, how fault tolerance is into the picture? Like, let's say if you lose a node, or if you lose a machine, then the data on that node is gone, right? If you don't replicate, how that scenario is handled. I think that's why HDFS has that replication policy.
And I think, I mean, these solutions also, for these in-memory solutions have that same, several nodes will hold the data, in case you lose one, you don't lose the data.
We actually had a lecture here on HazelCast, I think in the last year or so, which might be on video if people want to see it. But yes, the main idea from what I remember HazelCast is that all of the data is duplicated on some machines, but none of the machines have all of the data. If that makes sense. So the idea is no machine's burdened with all of it, but there are duplicates spread around. That's the whole point, is that it manages that duplicating. So when you lose a node, it notifies the other nodes to take over some of that duplication burden.
Yeah, that answers.
Much like different range levels. How many drives hold your data? Well, enough that you can rebuild it to get one that goes bad.
Hopefully it does a better job
Completely
than
mirrored. Okay, so here's some manageability patterns. So now you got the idea with the cloud is you got a huge number of machines, right? How you gonna manage that scale? With that many servers coming and going as you're elastically expanding and contracting, it makes it tough to find a node with the services you depend on, synchronize that state across those nodes, and then keep all those nodes configured. It can be a headache, right? And as you're building your app, if you one day want to grow into the app, into the cloud, those are the kinds of things you want to make sure you're thinking about going forward. So finding services, or service discovery, which is the official term here, not to be, it gets kind of overused, but when you want to find a service, and when you're in the cloud, finding another local service used to be done using DNS, right? Just ask DNS, where can I find this machine? Well, the problem with that is, in elastic environments, your cached DNS results are old hat. They're quickly out of date. Machines coming, going, you try to go to a service, that machine's not there. And it's too costly to query for the latest and greatest. So that means if I have to ask which machine is holding this, and I have to go make a query for that before I can make a call, it's really slowing down my system. So the answer that several solutions have come up with is, hey, in the background, we'll have some process that's keeping track of which nodes have dependent services. And so when you ask for it, I've got it. But that information is kept local. You don't have to go keep asking. So it's a little service that's running. So to handle that, there's some implementations. Google's Kubernetes has a deal where you can ask an environment variable for it. Where is this service? And it'll tell you. And it'll tell you a machine has currently got that service on. Now, there are going to be many, many machines that will be holding that service and serving up that service. So they do it by an environment variable. Hashimoto's console uses DNS or HTTP. I kind of have a heartburn with DNS because the people that might point to that DNS might cache it and then cache that answer, and then you start caching, you're right back to the same problem. But it does adhere to standard interface with folks who are using DNS. So I guess as long as you're hitting a local console agent on your box, you should be okay. SkyDNS does the same thing, and it does it on top of etcd, which we'll talk about in a second. And then, if you've just got a pure Java system, use Netflix Eureka. Netflix is open source, some great libraries that are all about, they're all done in Java, and all about scaling. So, another part of being able to handle that scale, all those machines, is how you can handle configuration. And from a manageability standpoint, that information has to be synchronized across the cluster, and even as it scales in and out elastically. So, if the machine goes out, it's got to be kept in sync. The availability, you got to make sure it's always there. Take that back, that's not what that says. This is about making sure your system's always available. So addressing the availability issues, you want to make sure your configuration updates your application without having to bring your application down. So it's notifying, it's propagating instantly to every machine that's running that service and notifying without having to do restarts. Okay. So we'll talk about some implementations here. So this is a kind of a two-part problem. The first part is, I've addressed here, is the dynamic updates to your app without shutting it down. Netflix ArcAeus provides a JMX interface, so you can use standard managed interfaces like you would do in your Java application with typed values. It needs a provider of some sort. And then out of the box, they provide the Apache Zookeeper as one potential implementation of storing or sharing that configuration information across the cluster. So this is, Zookeeper keeps that, replicates that data across the cluster. Netflix ArcAeus uses that. if you happen to look at etcd, if you're using a Linux system that's running etcd, it does the same thing. It's a service that, much like the /etc directory in Linux, or in your Unix world, keeps your configuration. etcd is a way to do that distributed across a cluster. So all your configuration goes out there, and that's what's being used a lot in a number of systems. Kubernetes depends on this. I think on the previous slide, I meant to say somebody else is backed by. Going forward, hang on. All right. Anyway, so it's a very common technology, cool technology. Okay, so let's talk about some resiliency patterns really quick. Who here uses, is aware of the circuit breaker pattern? Okay, old hat stuff, right? So clearly it doesn't just work in the cloud, it works everywhere. You specify some fallback strategies. If you run into a problem, it will take one of those other strategies. And Hystrix, which we'll talk about in a second, has multiple ways of handling that. Another resiliency pattern is around caching, where you keep a lot of your data cached that you might depend on in case the system you depend on goes down. So let's say you've got some REST-based microservices, and they talk to another REST-based microservice, maybe down the line, and that other system goes down. Well, until you can get it back, at least you have, if you've been using an HTTP client that has caching, you can use a lot of those cached results. They're not pretty current, but it'll give you something when you have nothing.
Can you give some examples for this?
Sure. So if you set up your REST-based interfaces, and that's the beauty of REST, right? It follows HTTP. Instead of having all the local SOAP brought it says, hey, let's leverage what HTTP provided, which was a lot of caching, right? Proxies and proxies, caching proxies. So if you are always calling for this one resource, by a unique ID, then if your system goes down, when you go to call for that resource, the dependent service you depend on, when you call for that resource, you'll have the cached one still. So if the call fails, you go, okay, well, I've got this cached version, and you can make a decision at that point, do I want to use this cached version to proceed, or do I throw an error?
So I'm just wondering who holds the cache?
The client, actually, it's just like your browser.
So each microservice has its own
HTTP client, yeah, that then connects to the back, to a service it depends on, right? And then we have that cache. And you can do multiple things with that, right? You can, we can talk about it here in the next one. Certainly you're going to reduce your costs by reducing your bandwidth required. So, yeah, so in this case, I use the Apache HTTP components, and you can get it configured so it will cache. And the key is that you can use some kind of store behind that cache. If you use a distributed store, then all other nodes will have that cached without ever having asked for it. Yeah, and there was that with Hystrix. Lots of options there. Okay, so this is what the Docker folks are here for, and I'm going to defer to you guys. Please correct me where I'm wrong, but I've used it a couple times. I found it very powerful, and there's some interfaces with Kubernetes. So when you want to talk about virtualization versus containers, do I want to run this in a virtual machine? Do I want to run a container? Of course, containers are hot right now, but I've seen numbers like this. You get a 9.5 times more efficient CPU at steady state in a container than you do in a virtualized machine. 6 times less disk usage, and I'm sure that's in systems that use copy on write. File systems will only make a copy when you go to write if it's changed. If it hasn't changed, of course it doesn't. And then and Docker has a 2x higher file I/O with random read and write. This is according to over KVM. according to an IBM presentation on YouTube. And I'll have these slides up and the hyperlink is valid, so you can see that presentation. So here was a Linux journals had a provisioning time comparison. And so, I guess in the bad old days when you had to provision machines by hand, it would take you 8 to 24 hours, and those would be completely stateful systems. That was their estimate. Then they say, well, with virtual machines, you're looking at 5 to 10 minutes, but you still have a very stateful system that stays maintained. But with things like with containers, such as copy on write, you get much faster times, 5 to 10 seconds to get it up and running, and it's stateless. So,
I'm not understanding what the state is that you're referring to.
So the way Docker works, and maybe someone can will correct me here, but you're building it in layers. It's not necessarily maintaining the state. You have to go to additional effort to try to maintain the state of the system. So if you want to, if you lose a node that's running your application, it's automatically, you can have it redeployed and have the same kinds of applications installed and running, but you're not really maintaining state. There's a separate thing for your storage, somebody help me here.
Volumes.
Where you keep your storage.
Volumes.
Volumes, thank you. Where you can keep state, but it's not kept in the
So
machine.
when you say state, you mean basically what the kernel remembers itself, what the kernel knows about itself. Is that the kind of state?
It's more the state of, oh, well, you know, I've gone through and I've tweaked some config files, and then that was last week, and this week I've configured some more stuff, and now my system is in this very unique state, and getting back to a usable system after losing that can take a lot of work.
I was going to say, yeah, persistent data. In fact, it's good to think of containers as more like processes. And so just like processes, you can spawn multiple processes that all write data to the process from somewhere or something like that. So same sort of analogy with containers.
Thank you. Well put. Well put. Anybody else?
So is that like saying the RAM of the process is what's going to go away, and anything storage like hard drives, so like that.
Yes.
But on the cloud, very likely you want to run containers, you will run virtual machines, and inside those virtual machines, you will run containers. So you don't need to do this comparison. I think they are different. You go to Amazon, Amazon only provides, virtual machines. So you want to run containers on top of that, it's up to you. You cannot run containers on bare metal.
Right. Yeah, that's, I mean, that's so nice. You've got an option there. And do you want that load? Well, sometimes it provides some value.
I missed that. Was it
Yeah, was it
asking whether or not you could run containers in the cloud on KVM versus bare metal, or what was the question?
What was the question?
Statement, I guess?
No, what I was saying is if you run on the cloud, you will run, your containers on top of a virtual machine. You cannot run, your containers in hardware because, Amazon or Google or any of them, what they provide you is a virtual machine, and on top of that, you can run, containers. So you don't need, that comparison makes not so much sense, on the cloud because you're going to be running, virtual machines, and on top of that, you will be running the containers.
Some of the stuff, so like ECS versus
Yeah.
EC2, that's bare metal-y versus not bare metal-y, I guess, versus virtual machines, like you're saying. So
Yeah.
there's some cloud providers that do run Dockers in bare metal.
But
Right, I mean, I think.
Is that what you were saying?
Sorry.
no, I'm saying, very specific about cloud providers.
I think if you look at Google, that's absolutely what their target is, right? Everything as much on bare metal as possible. Most data center utilization.
No, they do the same thing. You get a cluster of virtual machines, and you manage that as a cluster with Kubernetes, and on top of that, you run, your containers. They do the same thing, Amazon and Google.
Yeah, to your
That's
point,
today.
actually, one of the drawbacks with virtualization using containers is security, right? So VMs give you that hard isolation security point, which I think is what you're talking about, where you don't want, if you're a cloud provider, you don't want to have a security break or something like that, where containers from one vendor's stuff can access data, another vendor's stuff, or something like that.
True.
Containers, true solution. I
You
think-
have to go out of your way and do a good job in setting up your environment to keep one container from walking on top of the other.
And that's where VMs actually make sense.
Yeah.
Well, and the other thing that the VM is under the guise of the hypervisor, that provides a lot of the management for the cloud providers. If they were to replace that and directly manage Docker containers, you can see where this is going, where you wouldn't necessarily need a VM. At some point in the future, you just have a Docker container managed by a Docker manager, whatever that is.
Yeah.
That doesn't exist today.
Yeah,
There's a
right.
company that actually does do that, Joyant.
Oh, really?
Yeah,
Yeah.
they released Triton, which
Okay.
is more zone-like than
Yeah.
it is Docker.
I don't know if they're allowed to run in the cloud that way, but, you know, like I know that there are certain cloud providers that just won't.
They are a cloud provider.
Oh, they are cloud
Yeah,
providers.
they
Yeah,
literally
right.
like their whole platform runs on their platform
Yeah.
in production, multi-tenant.
Perfect. And that's probably the direction we're going
And
to
that's Brian Cantrell,
Right.
formerly of Sun, right? And so taking Solaris, and I mean, Solaris had containers before there was a Docker, right? It's called zones, right? And before Linux had BTRFS, which still isn't quite ready for production. You know, Solaris had ZFS.
Yeah.
It's we're getting there. Linux is getting there, but you know, it's pretty amazing what's happened over all those years, and that we had a lot of money to focus on solving those problems.
Yeah, so the joint guys have Linux running as a zone, and then you run
Yes.
Docker images inside of that, and it's faster than VMs.
And I would highly, highly recommend Brian Cantrell's January talk at the Docker meetup over there. If you want to hear about flying ponies shitting rainbows in your hands, definitely check it out.
Yeah, ignore the part about where he calls Larry Ellison a Nazi, but, you know, on tape.
Anyway, see
Yeah.
the talk. I wanted that this.
Well,
Yeah, one of the-
and allow me to take us further. No, he's done another great talk called Fork Yeah, where he, for the Unix Association, and he talks about what happened when Oracle took over Sun. And, a lot of us, think
I thought the most interesting point from his thing was the fact that with their solution, they can actually saturate 10 gigabit Ethernet from Docker images.
all I was going to finish saying was, he says, never make the mistake of anthropomorphizing Larry Ellison.
Oh.
It's an amazing talk. If you get a chance to see it, thanks, Brian Cantrell. All right. So application containers, Docker started it. AppC is a new open spec, driven by CoreOS, jumped on the bandwagon by Google now. Red Hat. Anybody else recall who else is on this standard? Of course, Docker isn't really a standard. It's a de facto standard, right? But there's some things that are missing, like some security stuff that Nimrat was mentioning. So CoreOS has their first implementation of AppC called Rocket. It's been announced that something called AppSera's got theirs called Kerma. Anybody had a chance to work with any of these alternate application containers?
Just long enough to notice that the Rocket guys need a UX designer.
There's also Run C. I don't know if that's Docker's like now open
Right.
implementation.
And the Rocket guys are on board with that.
Yeah, everyone's supposedly. I mean, it's the Linux Foundation or whatever is on board with Run C.
Including Microsoft.
Yeah.
Which one was that?
Very cool.
Which one was that? I'm sorry.
Run C.
One second.
That's like basically Docker just said, here's a bunch of our code, go for it. And so that's being developed separately.
Okay. So, I just thought I'd take a moment to talk about Kubernetes. Kubernetes depends on application container. It manages containerized applications across multiple hosts and providing application deployment, maintenance, and scaling. And and this is straight off their website. It's a product of a decade and a half of experience at Google running production workloads at scale. Providing the best of breed ideas and practices from the community. So the beautiful thing is it's open source, it's portable, and for me, that's key. I'm not locked into any one cloud provider. I can run this system. I can manage all my applications. So I'll show you here. It's got self-healing. So if one of my containers crashes, it notices it, it brings it back up. If I say I want 5 running, it always works to make sure that there are 5 running of whatever is in that container. And then auto restart, auto replicate, auto placement, put it on the right kind of node that you want to run on. And this is the thing that solves the problem with microservices. It provides deployment affinity, so I can say, they refer to it as a pod. I want these things deployed on the same machine or same type of machine. So if your microservices can now all run in separate, isolated application containers, still on the same machine, so that they're going to be fast talking to each other. But one is not going to wipe out the other, right? Because you've got that isolation. So here's just a few of the components. Kubernetes comes up, it's got a master node, and they're using Salt to provision minions, and I'll show the minions in a second. It's got a thing called replication controller, and that's the deal that says, hey, I want to make sure there are pods, and I want this number of these pods running from this template. And in this template, here's how you make sure my application is running correctly. Here's the URL to my service. If you don't get this answer back, or if you're not getting a connection, then consider it dead and restart it. And then it's got the concept of service, and that's what we talked about a little bit ago when we were talking about service discovery. You define some services. It will automatically do load balancing across those services for you, or instances of your service. So you call into a standard external address, and it will load balance across the instances that are currently running. One comes down, the load balancer keeps track of that, adds it back in when a new one comes up on another machine. And that's where it provides the service discovery. So our master node then launches these minions, slave nodes basically, and in each one of those you'll have an application containers, Docker. I see now they have embraced Rocket. In fact, there is this little thing with CoreOS where they've got a lot of stuff to come out of Google. Google's now invested in them, and CoreOS is going to be commercializing Kubernetes.
Kubernetes is free.
Is it? It's
Yeah, V1 was announced today.
That's why I could only really use it in a prototype. This was not a production system. All right, so here's those pods we talked about that are basically on when I have a minion here, that's really a node. That's either your virtual machine, like we talked about, or it's bare metal, which has Docker running in it. Kubernetes has got the concept of pods, and inside those it runs containers containing your application. So here's a kind of a Kubernetes cluster, and one of the things I discovered, I'll talk more about CoreOS in a minute, not just the company, but the actual OS. So you've got your node, you've got an OS. This is like ESXi if you're talking about VMs, if you're talking about VMware. This is just an underlying simple OS. And then in there we've got our master nodes that are running our Kubernetes components. So one of the things I found very useful is I wanted to be able to do this from my desktop. So I leveraged Vagrant. Vagrant is just a scripting engine, a way to script VirtualBox if you haven't used it. So we say Vagrant up, and it brings up 4 instances of VirtualBox, and each of those running some OS, and then on top of that, and I've overlooked the whole where Docker fits into this on this display. So there's one machine, but you get to play in it just like you're really on a cloud. It's local, so you don't have all the burden of sending stuff around. Okay, so that hypervisor OS I was referring to, CoreOS. There are kind of 2 of them going after this right now, CoreOS and Red Hat Atomic. Anybody here from Red Hat? Anybody work with Atomic? Okay. Anybody here work with CoreOS? Yeah? What'd you think?
What?
What'd you think?
Well, it's, as you said, it's fit for a mission, which is, if you are going to run everything in containers, you don't need all the other stuff, which is an operating system, and that you need to update constantly and keep up to date. And you don't need to deploy applications, because your applications are going to be running on your container. So it's just a basic, operating system. It's fit for a mission, which is, we love Docker, we love containers, we're going to run everything there inside that. So why all these other stuff?
Why do we need anything other than? Yeah, so it's part of this just enough OS, right? It's just enough OS to run Docker. And the nice thing about CoreOS is it's basically an evergreen, like your browser, right? It's always keeping itself up to date. So it's got a very current Linux kernel, and as patches come down, it keeps itself up to date. And
it's a small memory footprint. It's very small in memory, and it's very fast.
Yeah.
Very fast. You can see if you compare with other. It's much
I've
faster
actually
and
done that
smaller.
comparison.
Yeah.
If you go to the Kubernetes project, and there's different ways you can implement this. You can have it running on, I think the one I was trying was Fedora. And in comparison, CoreOS is small, it's fast. I think I saw something in here, it was like 115 meg. Allows you to even pixie boot that over the network, right? So you're going to go from Metal to CoreOS, which is suddenly then you've got the Docker environment. It is kind of interesting. It is a stripped down fork of Chrome, Chrome OS, which itself is based on Gen 2, but it's got read-only system files, so you can't, application services can't overwrite those. You don't need to. You're running in containers. Everything's isolated in containers. So it's just enough OS to run Docker, and then your apps each will run isolated in containers. And they're using the latest systemd that's coming along with the greatest versions of Linux. Of course, Docker. They are behind etcd, so it's key to it. That's how you can manage a number of these. It's really intended for cloud-based solutions. But if you're using Docker, there's a whole boot to Docker tool if you're running on Windows or Mac, just for a development environment. It's fairly easy just to use a VM because boot to Docker is really, it's VirtualBox with tiny core Linux on top, so it's very small. But I just go ahead and use VirtualBox with CoreOS, and it's very fast and more useful. I was getting boot times like 5 times faster with CoreOS than trying to get something up and running on Fedora. So I think Fedora's coming down, and then it's trying to bring down its latest and greatest updates that it needs, whereas CoreOS is already just up to date. Okay, so we've gotten a lot of talking. So this is kind of the, hey, where does the future lie in this? Which is things to think about. And I think, to me, it's pretty clear that we see more uses of containers. It's a lot less overhead. And I'm sure a lot of the Docker guys might agree with that. I can't help but wonder, and this is just speculating, right? Does VMware go out and buy Docker or CoreOS? Or both? I mean, it's a very cash-rich company. I would. It'd give me a big, leg up in some very fast-moving technologies. If I could invest in Docker or CoreOS, I definitely would. Okay, so this next one, I was going to go into a lot more detail on this little fanciful idea iPad. I didn't have a chance to really diagram it out, but what we're seeing is this sun setting on Moore's law, right? We keep getting smaller and smaller and smaller now. Intel's having a hard time getting out the 7-nanometer chips that they talked about. So it's the 10, but no, that's being delayed. So there's appears to be this physical limit that we can't seem to, that we're running up against. So if we talk about what the cloud was, it's a redundant array of hardware. What happens if we start talking about our phones, the system on chips that are so cheap, right? Your Raspberry Pi, that's ARM system on a chip. So what happens if you take a bunch of those and that you start making your data center out of that? It uses a lot less power, right? A lot less heat. And as those get smarter, smaller, I think there's a lot there. You know, we're beginning to see ARM-based blade servers, right? But I've got a friend out at Expedia. Anybody here with Expedia? No? Okay. Anyway, he was saying, we're really thinking about just taking a bunch of Raspberry Pis and setting up a box. We don't have to go into the cloud with it. Just something to set up our cache, but a bunch of them in a box. And if you look how Raspberry Pi works, the chipset in there is, I think the Raspberry Pi 2 is like 40 nanometer. And that's why it can be so cheap. None of the other chipsets being created now are big old 40 nanometer, right? That's really large. And so the facilities that produce those 40 nanometers were paid for long ago. It's been, went through 40 nanometer, blasted up down to 27 and below. So that's why you can get Raspberry Pi so cheap. And we're seeing other hardware. I forgot the name of it.
BeagleBone?
What's that?
BeagleBone?
BeagleBone is one. There's another one that's right now they're $35. It's 27 nanometer. It's out of Korea. Anyway, what's happening is now you got 27 nanometer facilities that are been paid for long ago, so they can produce this stuff cheaply. And at some point, Intel's kind of stopping there on the CISC-based stuff, and RISC is finally get down smaller and smaller. So it really makes a lot of sense to me to see cloud-based ARM, but system on a chip. Because not only, if you're using this horizontal scaling, the more of those system on a chip you throw out there, each one of them is coming like with a gig. If you're horizontally scaling, you got more memory now. Each one of them is also coming with a GPU, right? So there's a lot you can do with a GPU in terms of computing. So anyway, it's fun to think about, right? Where is this headed? And anyway, here's the takeaway message. These libraries and stuff are useful anywhere, not just in the cloud, right? If you're thinking about how you can scale, and you don't have to embrace all of them at once. You can evolve your system to embrace these. All right.
You didn't talk about Java environments. What's it take to be running Java in containers?
Oh. Anybody want to?
What?
What's it take to run Java in a container?
Doesn't matter.
So all you have to do is you say, hey, I want this. When you're defining your Docker container, you say, I want this version of this OS. Right? Right now it's just Linux, but some version of some Linux that may already include Java. Or if it doesn't, you can set up your Docker file to install.
Preferably one that has a good package manager, so it's just one line of strict instructions to get it to install.
Right, but you
Not
can do like
curling
a
from Sun or
run
from
Ubuntu,
Oracle.
Yeah,
and then
like
you install on
an
Java and
apt-get
then you
or
run
a
it.
yum or something like that. Yeah.
We get
So it's very simple.
So are you running standard Java inside that, or
Yeah.
are there
Oh,
any
yeah.
restrictions on it?
No, I mean, what it is, when to think about a container, you have to think about, it's about isolating, it comes from BSD jails, which says, hey, I can't use more than this much CPU, I can't use more than this much disk space, right? So it's assuring that this application does not walk on this application. So it's basically bare metal, it's just nicely cordoned off. That's it. Everything you can do in Java, you can do in Java there. Shoot.
Yeah, whatever runs on Linux, for example, runs in a container. No change. You use the same libraries, everything is the same. You might need, to do some configuration in terms of ports and that kind of stuff because the container requires some configuration for ports and a few other things. But out of that, all the libraries that works for you in Java works in a container, all the tools, everything.
Oh, yeah.
Java versus other languages, especially Go. Have you looked into that, sort of the future, we're talking about the future of really the abstraction, I see it. So along with the abstraction, presumably the languages are going to change. Do you think it's going to change towards Go, or stick to Java, or be something else entirely, or be JavaScript?
I'm not unbiased in answering this, so.
Anybody else?
I mean, as languages go, Go doesn't appear to be as elegant as Java in some ways. But you gotta see who's driving it, right? So you got a lot of Google resources pushing Go, and there's some advantages to having statically linked applications.
Joyent is behind Node, so there's
What?
that.
Joanne.
What? You gotta take it away from
It's not over.
All right, and so did that answer your question? Then I get you, George. Yeah, I mean, I've looked at some Go, wasn't, for Java.
I think to me, like, Go is more systems language.
Yeah, Go is
versus high level business language.
Yeah, I think that's fair, right? I mean, a lot of these tools, NCD is written in Go, Kubernetes is written in Go, Docker is written in Go. Yeah, that's right.
We're still in pre-production, but we're running the Java 8 container. I found in a public repo. It's just named Java 8. We're running Scala code on it. It runs great.
Does it? Yeah.
George.
So on one of your earlier slides, you talked about moving things to different boxes based upon scalability. Scalability means we recently had the experience that our normal box has Apache, PHP, and a large Java client. And we had a PHP memory leak, which basically meant because of the way Apache works, we had 50 Apache workers, each using more and more memory, but none of them were big enough to be the largest kid in the room. And so when the memory started to run low, Linux looked around for the biggest kid to kill and killed Java. And we're sitting there going, why is our Java server suddenly falling over all the time? So we are literally moving the Java off into a separate scale group from the Apache one, because of course, once the Apache leak starts to happen, it starts killing off workers, but they come back. Java didn't.
Another thing you can do, you run containers, you can run different HTTP servers in different containers, and then you isolate different pieces of
Yes,
application.
but I thought the containers consumed the host memory as they grow.
I'm not sure.
Yes,
We need to learn
because
that.
they're processes, they're just like processes, so they do consume the host memory.
Right, so this would have caused it to kill Apache there, because if all the Apache threads were running in a single container, that would have been better, I guess.
But if everything was in a separate container, it wouldn't whack the Java process, because that would be a separate container from all the Apache processes.
No, but I'm just saying the Java container would have been the biggest kid on the block when the whole host started running out of memory.
No,
Not
but then
if
you
all
have
the
a
Apache
secure
were
management
containers.
service that manages containers and does all that, so. At the OS level, the OS does that, but. Are you talking about the Linux host OS itself?
The Linux host OS kills the biggest kid on the block when it was running out of memory.
It's interesting, I wonder if it would kill containers or that. Well, it would probably kill Docker
I don't know.
itself.
I think it's a good point from you guys.
But it's a good reason to not necessarily mix your environments in a single box.
Yes.
Go back to the whole need for containers, right?
The problem there with PHP.
Profiling and debugging.
I'm sorry, okay.
Sorry to
Go ahead.
So about horizontal scaling, what's the next bottleneck? Is it database? That's where things will get saturated. I'm just thinking like, okay, you are adding more boxes. Where all that, like what's the next problem to solve? Is it like database the problem that you have to go for NoSQL databases, or still a relational database can scale to where we are scaling in the cloud?
Yeah, I mean, I think, yes, right? You can throw more hardware at that problem, but are you, you have to keep in the mix networking, right? Okay. What I recently read an article where Google is creating their own, really fast networks, because that's where the big bottleneck was happening.
If you're using microservices, are you putting all of your data into a single database?
Yeah, like
Yeah, it depends on-
there's no
That depends on your use case.
how micro
There's
are
no-
your
there's no one
microservices
answer.
if they have to write to the exact same data
Yeah.
store?
Well, that's what we're doing.
Well, that's the interesting thing, is that they enable you to raise or lower the level of abstraction, depending on
Right.
the use case. And
Right.
scale things out without having to code the scaling code within your application.
Sure.
Cool. Anything, anybody else? All right, thank you for sitting there so long.
All right, so,
Not really, no.
books, you want to do the honors? Okay. Let's see, let me actually turn the camera off. I don't think the online audience cares too much about this.
I don't know much about Python.